Yes.
Good morning. Welcome all to the seventh and last session of the International Virtual Forum on TB, FoVI-TB 2022. Before we begin, I would like to inform all the attendees and panelists that this session is being recorded and is being streamed on Zoom and simultaneously on YouTube, Facebook, and Imagen TV UBC channel. We have a YouTube channel in Spanish, which is Divulgare ECS UABC, and another YouTube channel in English, which is Remi TV. The transmission of this event throughout the different channels is done thanks to the support of the Audiovisual Production Study Center, CEPA, from the UABC, to whom we appreciate for their hard work. This forum is done thanks to the support of these institutions, the Health Science School, through the internalization program by the University of Baja California, U.S.-Mexico Border Health Commission, the National Thematic Network of Border Health, the Multidisciplinary Network of TB Research, REMI-TB, the National Control Prevention, Disease Control and Prevention Program, SENAPRESE, from the Ministry of Health in Mexico, as well as the National Network for Prevention and Control Research of TB in Mexico. This International Virtual Forum on TB 2022 has the intent of opening a channel communication for sharing scientific information, having international and national collaboration on biomedics regarding prevention, diagnosis, and treatment of TB, with the goal to meet the goals set by the WHO as part of their tuberculosis strategy. The strategy tries to reduce 90% the number of deaths due to TB and 80% the incidence rate for this disease by 2030. Regarding the baseline, which was 2015 data. TB, unfortunately, is still one of the infectious disease most lethal around the world. Every day, over 4,000 people die from TB, which can be translated into 3 deaths per minute around the world. It's important to remember that TB can be cured if it's detected on time and treatment is completed. Likewise, we'd like to remind you, to those who are here with us, we'll be issuing attendance certificates. So please, you can check the terms and conditions on www.remitb.org. And also, for those who have not logged in yet, you can go to the same website. You will find a link to fill out the form, or you can also use a QR code, which will be appearing on the screen throughout the sessions. You only have to log in once. Now, I'll pass the floor to Dr. Ricardo Perea Jacobo, who is a professor of science school by the UBC in Ensenada, who will be moderating today's session. Dr. Perea, the floor is yours. Thank you, Doctor. I would like to introduce the first speaker for today's session. Dr. Rogelio Hernández Pando, who studied at the Autonomous National University in Mexico. He's a specialist in pathology by the General Hospital in Mexico. He got a master's and PhD on basic biomedics research on the immunology line, was graduated with honors by the Biomedics Research Institute by the UN. He has a postdoctorate in immunopathology by the Microbiology Department of the Pathology School in the University of London in England. Currently, he is a researcher by the Medical Science College and also leads the section for experimental pathology by the Pathology Department in the National Institute of Medical Science and Nutrition, Salvador, Zubirán. Today's presentation is titled Neuroimmunoregulation on Experimental TB. Dr. Hernández, you have 40 to 45 minutes for your presentation, and then we'll have 10 to 15 minutes for a Q&A session. Thank you. Oh, thank you for the introduction, Dr. Perea. And I want to thank Dr. Raquel Muñiz because she invited me to be here with you. Well, my intention here is to talk about, show you some of the trials that we have been doing for quite some time, trying to set the relationship between our both large systems that allow us to respond to environmental stimuli. And this we have. These systems are the central nervous system and immune system. It's important to see that there is should be very constant and good communication between the two. You could also see that it's a single system because neurons can produce cytokines, and the immune systems, lymphocytes and macrophages, they also create neurotransmitters. So when there is a stimulus, an important such as MTB infection, and then we have a series of elements and physiological elements that are related between the two systems that obviously have the purpose of eliminating these agents. So in these two major systems are the sympathetic nervous system, but also the parasympathetic has plays an important role, and hypothalamic pituitary adrenal axis, which also plays a very important role. These systems, we have been able to study the systems, and regarding the relationship that we know, it's very well characterized for the lung, which is an organ that has so many nerves. They have seminal nervous endings, and in the case of vegetal term endings, we have the motor vagus. It also has on the bronchi walls. I can't hear him. He's back. And so the dilatation and contraction of blood vessels and the bronchi walls, and the production of mucus this takes place here. So it's very important to mention that it's something that has been recently discovered and studied, is that there's large communication going from the lung to the brain through the same nervous endings. This is basically the motor vagus. When there is inflammation to the central nervous system, and of course, the connection that we have with the hypothalamus, which plays a very important role to be able to regulate the constant communication process between the brain and the lung. In this regard, we have been studying this relationship using the experimental design on mice, biopsy mice, and which use the microbacterium, which is H37RV. We use a high dose to produce a progressive infection, and as you can see here, we have sacrificed animals at different dates, and we study different techniques to look at the lung and see what was the immunological response to this, and what are the immune responses that allow the control of such a disease. So in this model is very well summarized. It is an early phase that is for the first month of the infection, and here we have an important contribution of the immune macrophages, TNF producers, IL-1 alpha. So in about 2 weeks after the infection, they have the Th1 producers, IFN gamma, they have a great impact on the progression of the disease. So throughout this first month, there is activity from the innate immune system. After the second month, after 30 days, and up to the 4th month of infection, the animal goes into a progressive phase. Here, the Th1 activity drops, IFN is reduced. Also, macrophages, they start producing less cytokines, IL and TNF, and now they produce more TGF-B anti-inflammatory cytokines. It is important to remember that we have to say Th2, they will produce IL-4 and IL-10. They go up. And so we have an anti-inflammatory environment. See this from the histopathological standing point. It is related to progressive pneumonia, also have fibrosis, and they have necrosis. They have a great increment on the bacterial load, and animals die due to respiratory deficiency. And this is what happens on this progressive TB model. Well, here we start checking in the vegetative nervous system, particularly the sympathetic branch, as you know, is represented by some nervous centers in the brain, and also the lateral columns by the spine, going from the thorax to the lumbar area. So the system has an increase, plays a very important role throughout in all the body and also in the lungs. So here is where we can see that regarding this, we have the production of catecholamine synthesis is impacted. We know that norepinephrine is one of the most important neurotransmitters. We go to sympathetic endings, and this neurotransmitter is produced from tyrosine. And the key enzyme for the production is this enzyme, dopamine hydroxylase, which is also a good distinctive marker of this production activity in this neurotransmitter. So here it's also important to remember the leukocytes, they have receptors for these neurotransmitters. They are divided into different groups, alpha and beta. Alpha are divided by 1 and 2, beta also divided in 1 and 2. As you can see, the naive cells, the virgin cells, those have not differentiated completely, CV8, and they express basically transmitters of the beta-2 transmitters. The Th1 cells produce basically B2 and B1, and interestingly, Th2 cells, they don't express any receivers for this. So, which is a very interesting condition. So they don't have any response capability for this. So it's also very important to mention what is the kind of response that we have on the lymphoid cells before these neurotransmitters. When a naive cell is in contact with other substances, which doesn't make them more sensible, so they can differentiate with these Th1 cells. And in consequence, they can have interferon gamma production. When Th1 cells are completely formed, this is a determination for working as a Th1 has also been well defined. So at this time, the catecholamine is higher the presence of the antigen, and they're going to produce less interferon gamma, or nothing will happen if the antigen shows up later on. So it's important to have this concept in mind, because So we used to think that there's a dogma to think that the tocopherols were always suppressors of the cell immune response. But now we know that the activity depends greatly on the level of differentiation between the T cells when they're in touch with this neurotransmitter. As for macrophages, they also have receivers here in the beta-1 and alpha-1 and alpha-2. It's important to see that this related to the alpha receivers, and they have a stimulating effect to the macrophages. So they have production of cytosine pre-inflammatory cytokines. When this is related to beta receivers, they have an opposite effect. They suppress the activation of the macrophages. So it's important to remember that both macrophages and lymphocytes, they can produce so they have a tyrosine hydroxylase, and consequently can synthesize and release and degrade. They have MAO, which is a key element for degradation. So when this background, then we some time ago we did a trial where we assessed in the model that just showed you what was the production of catecholamines in the lung and in the brain, particularly in the hippocampus. And as you can see how in the hippocampus, we have a high production of this substance, and it goes up. The terminal HPBC, it reaches its peak on the 14th day and then drops. We saw the same in the lung. And lungs, we see that because of the baseline, we produce quickly, indicate how it reaches the peak. And it's a very important day because it's a day when the granulomes are formed. So it's the key start of the activation of the acquired immunity. So it's a very important day. And also, as you see in the case of brain, and the lung also drops drastically. Its concentrations drop even below non-infected animals. So what's the origin, what's the source for this? It's very important to see here. You see here, when we did the detection on the tyrosine hydroxylase, we have this as in this animal that has been infected for 14 days, and you see several positive cells around the blood vessels, some granulomes, which are nodes that do have no necrosis, and you see humans, and we see that all the lymphocytes, but also macrophages are here. Interesting enough, the lymphatic glands that I can show you one of those, they have a lot of positive cells to tyrosine hydroxylase. So we see that there is an active synthesis in the cells of the immune system. As for the receiver, we see how also around blood vessels, most of the lymphocytes are present. They show positivity to the TB2, and then because also the macrophages and lymphocytes, and they have high positivity. Interestingly, on the 60th day, when this disease has been based and it has, we can see how the pneumatic areas, there are very few cells that are positive to tyrosine hydroxylase. So there are very few that synthesize, very few express the receiver. So it's basically in the early stage of the infection when we have this response. So what we did later was trying to evaluate the type of response. We could see, physiologically speaking, having antagonists. And for this, what we used was this drug, which is 6-OH dopamine. And it destroys these endings in selectively. only the peripheral endings. They have no effect on the central system. So the base effect is in the periphery, and they also use formoterol, which is an agonist. So we try to evaluate mosvinamol for a more physiological standing point as a contribution on the development of the disease. Interesting. It's very interesting that when we use the drug that destroys before the infection, this is the day before the infection. So in fact, the animal 1 day after this medication is administered once a week. So we see how in the progressive stage, compared to the control animal that only received the vehicle, the animal which we destroyed this termination, they have many more bacteria. They also have a lower extension of pneumonia when we measure it. And this is completely opposite to what we have when we use an activator to the response, especially when we started the treatment with formoterol. We stimulate. You see how after treatment there are more bacteria in animals treated with these stimulators against the control, much smaller against those where we eliminated the response. So obviously we can see this very clearly. And also that is fascinating is when the lungs of these animals, we use it for RT-PCR, and then we try to assess the transfites on the messengers from the cytokines and this disease. So we see here on the black bars against the white bars, which are the control. The black are those treated with 6-OHDA. And you can see how there's almost no production of TNF. There's almost no production of INF, no production of IL-12, IL-17. And what we see here, basically, in the first week, high production of anti-inflammatory cytokine, which is IL-10 with the formoterol. Basically, in the progressive stage of the disease, the IL-17, the levels of IL-17 are very high. So there's a very good correlation regarding the release of protective and non-protective cytokines. So when we use formoterol after the 60th day, we have an effect which is basically the same as what we had in control. And then we have the granuloma. We have higher increase versus the destruction of the terminations. So the effect is basically in the early stage of the disease. What we see in this model, when we infect a lung, we have the activation, local activation in the lung. So it takes the stimulation, nervous stimulation to the central and medial area of the brain, nucleus cerebrus, and then from here we have the afferent response, which basically stimulates locally the response of the new adrenaline. The new adrenaline starts to bind to the receivers and the lymphocytes and the naive lymphocytes TH0, and they produce the TH1, and then the same TH1 and the macrophages start to become independent and they produce ectopically adrenaline. So the lung becomes rich of this neurotransmitter, and they have a good transmission of the parallel immunization of the bacteria, particularly of the immunity. Okay, but the other important branch of the vegetative nervous system is the parasympathetic branch, and this one is basically presented by the vagus nerve. Also, on a lung level, they can perceive. It's like a sentinel system that has receivers and TBR type receivers. They can identify the bacteria, and they also have receivers for TNF. So through this stimulus, there's an afferent activation. It goes to the central nervous system, basically the part that has to do with the hypothalamus. And from there, we have the activation of the dorsal motor nucleus on the vagus nerve, and then the brain sends a stimulus to the lung, and that stimulus is gonna produce the vagus endings, release these immune cells, but basically the macrophages, they have receivers for ACH. Also, basically the alpha-7 receivers. These are lipothymic receivers, because there is another kind that are the muscarinic receivers. These nicotinic receivers, they have an impact on the joints. The ACH and the receiver is to inhibit the macrophagus. It has a potent anti-inflammatory agent. So now it's what we call a reflex. Vagus nerve lung reflex. So this avoids excessive inflammation in the lung. So we come up with a similar strategy, and this experimental model, we quantify the ACH and different dates of the infection. Here you can see how since day 1 they have the release of ACH. On day 7 they have a peak of high elevation. It maintains steady, especially on the 60 days on the advanced stage of the infection. There's more ACH in the lung. Completely opposite acetylcholine. So if we see which cells are maybe producing this ACH, the transferase enzyme, we see here on the day 7th, right here, the main source seems to be the bronchial epithelium. It's highly positive. We have some macrophagus here, and also you can see some uniform lines that may be nerves. Interestingly, on day 14, we have the granulomas, and we have positive macrophagus that synthesize ACH, and also macrophagus produces ACH. And what's completely opposite to the other system is the advanced system of the infection. And day 16, basically the macrophagus, basically in the pneumonia area, are highly positive. So this high concentration of ACH on using this technique is because macrophagus are being built with high production of this. They also express they also have the expression of A17R. So the cell produces a factor for which they have a receiver, and then they can respond to this receiver. So here we see macrophagus and lymphocytes on day 7 are positive. In the granulomas areas, there are not many positive cells, as you can see, but we have many of them on the pneumonia areas on the 60th day. So clearly on day 60, when there is more pneumonia, it's important to have an anti-inflammatory effect, trying to avoid a higher number of inflammatory cells in the alveoli, and then this contributes to hypoxia and the lack of oxygenation of the tissues. So it's very convenient having less inflammation. Apparently, with what I'm showing you, the cholinergic system is very important for this process. Once again, we did the same strategy. Now we use blockers for the nicotinic receivers. So we used a receiver, an antagonist for the alpha-7, and so also for the beta-4 receiver. And here we have animals treated with on day 6, as of day 60. That's when we started, and you can see how the result on the advanced phase against the control, the non-treated control. The animals were with supreme suppress the efficiency of the activation of the acetylcholine, and I mentioned it supprimes the macrophagous activation, and it's very evident how the number of bacteria is dropped. And it's also clear it has a beneficial effect as the anti-inflammation, the reduction of cytokines, interferon, and so on. And obviously, the cholinergic system is like a double-edged sword. On the side, it protects the excess of inflammations to protect the functionality of the lung, but on the other hand, it favors the growth of the bacteria because producing the activation of the macrophagus. Consequently, when we suppress the cholinergic and the receiver end, we see how the number of bacteria reduces significantly. But it's very interesting how pneumatic inflammation does not reduce. As you can see here, how against the control, these are the pneumatic areas that are constantly consolidated right here. Is very similar to animals where we blocked their alpha 7 and beta 4. So we also have a very evident correlation with the cytokine expressions determined by PCR. And control animals in black, animals were to suppress the ACH. They have much more production of TNF alpha, higher production of IFN gamma. They have more production of NOS, and they have much more production of IL-17A. So this explains why we eliminate so effectively these bacteria. So this also it makes us want to do some high immunotherapy trials. We infected animals, they let them untreated for 2 months, and when the animals in the advanced session of infection, then we'll see in lots of ACH we suppress the inhibitors and the blockers, the receivers. And at the same time, we give them antibiotics to see if we have certain effect of a synergic effect. And certainly there is such an effect. So we have the amount of bacteria, particularly here we see the bacteria only treated with antibiotic. This is the number of bacteria, the amount of bacteria, and this is around these levels. And they say for in different days of the sacrifice of the animals. And if we compare this versus when in addition to the antibiotics, we give them blockers. We blockers for the DHPA and MLA alpha. So there is a higher, a more pronounced reduction. So here pneumonia drops consistently, as you can see on the images at the bottom of the screen. So we would think that this could be some sort of a supplementation on the treatment. So we haven't tried this in human beings, but in the experimental stage, it works pretty well. So something that is completely fascinating is the fact that when we are looking at the possibility of having acetylcholine being produced by the bacteria, because this agent produces this production of acetylcholine, and we see that they are found in plants. And we think that it could also be present in micro and MTB. So what we did, we had some culture bacteria, basically. We determined by a ELISA test, much more acetylcholine versus animals that are in stationary stage. Also independent, also intracellularly speaking, all we have there are bacteria. That's the only thing that we can have. And there is a very important presence of this neurotransmitter, acetylcholine in bacteria. So all the bacteria produces. What is what good it does to them. So what we start saying is when we add acetylcholine to bacteria, when it incubate them with acetylcholine, we see then that there is an increase in the proliferation of, as you can see here, when we incubate them with acetylcholine, when acetylcholine for the bacteria is a growth factor, at the same time it's an immunomodulator because it activates the macrophages, as I showed you. And of course, when we infect macrophages with H37B, so we have acetylcholine, we can see that, and then well, it does not produce when the bacteria is dead. And when we use, the hypervirulent bacteria that is produced to the non-genotype, HARNAM, was isolated in Orizaba, in Veracruz, in Mexico. So we see the production is tremendous on acetylcholine and very against to the virulence of CTB, which is medium virulence. So may have an immunology evasion mechanism of higher production of acetylcholine. Okay, but so here are the different systems, how they participate significantly in the evolution of the disease. But these afferents, these stimuli, nervous stimuli, and that originate in the lung and they go to the brain, they can be kept chronically, because TB is a chronic disease. So when we study these in more detail, it's very interesting to see how the immune system also regulates changes synapses speed, surveillance of the neural cells, central oxidative response. We have some experimental models. They're very interesting, where we can see how tyrosine-1 plays a role in learning skills. So the cytokines at central level, they are related to very complex functions at the central level. And well, when we saw that what this meant from the neuropsychiatric standing point for TB, we see that it's very frequent to have this problem, alterations or neuropsychiatric alterations in patients with TB, fear, suicide attempt, 9% depression, 7% in males and 10% in females. Depression plus anxiety, very high, 19%. So this is basically with the patient knows that it has an serious infectious disease, and of course has a psychological impact and makes them depressed. That was the general concept, but obviously, and in mice, they don't know they're sick. So we studied this neuroinflammation at experimental level. And what we did here was we took the brains of all the infected animals through the trachea that are suffering pulmonary TB. And then here in the different sacrifice times, we explore the hypothalamus, the hippocampus, and the cerebellum for the cytokines production and the production of neurotransmitters and adrenaline, dopamine, serotonin, and of course, so what we found here, when we determine the first colonies in the lung, progressive, and in the brain, nothing. No bacteria grows in the brain. So there is no brain infection, at least not in terms of bacteria growth. And you can see here in the PCR what's happening. Pro-inflammatory cytokines, IFN, IL-12, TNF, in comparison with controls animals the same age, non-infected animals, and this in black. This is in the hypothalamus, the large amount of TNF mostly in the late stage of progressive stage of the disease. Also, in the hippocampus, since day one, it has high production of TNF, the same as in cerebellum. Same happens with IFN and IL-12. So these are basically an intense inflammatory response in the absence of bacteria. There are no bacteria in the brain. What we have is the lung infection, and that all those nerves that are being stimulated and they're communicating to the brain, and of course, definitely the cytokines are circulating in areas where there is no amount. They are going to the central level. So the patients and the inflammatory that are highly expressed in the brain is an oxidation phenomenon. So we have an expression of INOS, hypothalamus, hippocampus, and cerebellum for the nitric oxide synthase. And we also have, interestingly, we have the production of IGOs, activation of this enzyme, a tryptophan, which is a precursor of serotonin, and it translates into cholinergic acid. And cholinergic acid is a false neurotransmitter. It stimulates areas when the NMDA transmitters and generates hypercalcemic effect in the inside of the neurons of the brain cells, and it causes cellular death. Some consequence, we see here the neurotransmitters in the hypothalamus, hippocampus, and cerebellum. We see serotonin, dopamine, epinephrine, and norepinephrine. Comparing them against the black bars, you can see a large big reduction in all the neurotransmitters except for the norepinephrine hippocampus level, which is what I showed you before. But the rest is production of these neurotransmitters is being reduced. So there is a very important effect in the balance of neurotransmitters at national level and at cellular level. So we see stimulated in the same area the expression of mankinase, MAPK, this components P38 and J and K. So we see the densitometry establish how there is a high inspection of the system. G and K is relevant for the activation for the dactylase for the activation of genes and modify parasitosines. Then this high expression of cytokines for the nervous tissue is due to the activation of this. And this is also important, particularly for the P38 system. It's deeply developed to the neurotrophins, basically the brain B, D, and F. This growth factor, is fundamental to keep cells alive. It's a surviving factor. Hypothalamus and was in cerebellum, less in the hippocampus, and reduction on the production of ENS, very important to keep him homeostasis on the nervous tissue. When we see this, basically on day 60, we see the hippocampus. We see a number of increase in the this is normal brain cells. You can look at this. Here, the core is completely epigmatic. These are dead cells. You see the number of dead brain cells. In this area, for example, which is the C3 component, and the core of the hippocampus, that's where we see more brain cell death. So this is a significant number of dead cells. So it's important in the response for the nervous systems is doing to see how can it be translated for the neuropsychiatric alterations or disorders. So in this regard, we tested infected mice with the bacteria. So we measure the locomotor activity. And this tail suspension test, which basically what it tells us, we check the depression, check for depression. And this one is a stretch attend posture. Basically is related to the mood of the animal. You explore less when it's depressed. And also we just check memory, short-term and long-term memory. This is very hard because these are infected animals, so we have to do it. We need to be very careful and be trained for techniques, for neuropsychiatric techniques. Well, but we see the information that we get is very interesting. And animals at the beginning, they have an important issue for locomotor activity is reduced. They lose weight and they lose appetite. And that is what we call sinus behavior. And in Spanish, we call it sinus behavior. This is the sickness behavior. And that's when people feel they don't feel good. They have no energy. This is expressed basically in the first 3 weeks of the infection. And this continues for into the progressive stage. Also in that stage, as against the control animals that are not infected, the gray bars that are for infected animals with MTB in the lung or in the brain, they show depression-like behavior, anxiety-like behavior. They also have neurological severity score, and they also have alterations in short-term memory and long-term memory. So these neuropsychiatric alterations in patients with MTB, they come from the inflammation. It's not only the psychological effect, but it's also there is a damage at a central level. Some more advanced disease. There's even brain cell death. So this consequently leads us to this terminal scheme where we can see clearly how the lung inflammation from TB is captured. This information is captured, that is taken to the brain, and the brain eventually is going to be an increase of the cytokines levels and central level. This obviously leads to a reduction of the production of the neurotransmitters. And in the end of this course, this also leads to a reduction of the growth factors, which eventually get to the brains and to cellular degeneration. This has an impact on the neuropsychiatric aspect of the patients. So the vegetative nervous system plays a very important role. Cholinergic, also from the fear due to the bacteria they produce acetylcholine, which is a growth factor for them. And all this information, all this activation, inflammatory activation in the lung bulb. This happens since this is chronic. Also, the presence of high concentration of peripheral cytokine consequence an absolute imbalance in the production of neurotransmitters, and also significantly we're gonna see neuropsychiatric alterations in patients. So this is what I wanted to show you. There is more about the environment, but I don't have enough time to elaborate on those. So thank you so much for your attention. Thank you, doctor. for your interesting conference. Now we're going to have a Q&A session. We have many questions for you in the T cell response. What is the malnourishment impact on this? Are there any recommendation for a specific supplementation for patients with MTB? This is an interesting point that honestly we haven't studied, but obviously malnourishment will lead into cell brain death, because we know the nutritional deficit, especially in children, is a very important factor that what we call in pediatrics, the development of children, all this evolutive process. So obviously this is related to the inflammatory process and neurodegenerative processes. And then of course, it would be very interesting to come up with a therapy to address the situation. So let me tell you something about this. We have been successful in the use of little amounts of very low concentrations of dexamethasone through the nose in nose drops, nasal drops. It's the effect for this super efficient in this kind of cases. This is an cell immune suppressor. They said that this goes against the treatment, but actually in low doses and through nasal drops, they go faster, and this avoids brain inflammation. Another thing that has been very useful for us is a substance that we maybe could be supplemented with. This is curcumine. It's an antioxidant that is used in traditional food in India. The malonga, that's a scientific name of the plant, and has a great effect on to prevent central nervous system inflammation. This allows a better elimination of the bacteria at lung level. This has been published, and maybe I can send you a link so you can read more into it. So based on the sorry, what was that? Well, could you repeat that again, because I couldn't hear? Yes, it says, the question is, according to levels of the adrenaline and the lung and the hippocampus, is there any difference in the immunodeficiency cases? I guess in patients with some immune conditions such as VH1 and with AIDS. Yes, I'm not sure. I think that it hasn't been studied in humans, but the only group that I know that has done this neuroendocrinological aspects systematically is a group by the Rosario University in Argentina, Dr. Oscar Bultaza and Maria Luisa Bay. They have done a great job with patients getting cells in peripheral blood, and they have very interesting information about this. But basically, they have mostly done with different hormones, because I tell you that because we have worked together several times. But I don't know, I haven't seen any of their work for TB. They froze. He's back. Okay, the next question. Is there any trials abandoning this elevation and the predominance in the acute stage? I think you mentioned that towards the end, right? Yes, certainly. When we activate at the very beginning, in the early stages of the disease, there is obviously, all is related to the increase of the systemic activity for higher heart rate, higher breathing rate, higher metabolic activity. As you know, the adipocytes, they have this neuroprotein to do a degradation process for the fatty acids, also for the nucleolysis. So all this goes to adapting the body to the entire system so they can confront this infectious process. And in this regard, we see that how the vegetative nervous system is getting ready, is preparing us to be able to overcome the stress originated from all these systemic alterations that the most important, obviously, is simply metabolic. The process of energy consumption of finishing as such is as high as the one the other things from premise. In fact, so it's also, I think it's a great action going to respond with symbol. This FoVI-TB, as I have shown you, when at least in experimental stage, there is good impact, specifically promoting the differentiation of the different cells and eliminate more efficiently all these conditions. Okay, elaborate a little bit more on the same question. Most of the investigation had to do with the deal with brain inflammation, but which data could be a good method, non-invasive method to study this connection between brain, lung, and lung-brain connection? A non-invasive method. Okay, I would say, and generally speaking, the non-invasive aspects, and we have been trying to use them as treatment more than diagnosis. That's what for that we have done in experimental stage, specifically in animals. We have seen that by stimulating the vagus nerve, we can improve the bacterial elimination process, because as I showed you in the case of the blockers, the nicotinic receivers, we're trying the acetylcholine deactivate this. So there are some suggestions here. Fundamentally, start by connecting electrons, ganglions, and then they stand gland, and they get this kind of response. This has been done for other infectious diseases, as well as for TB. They might have some therapeutical effect. Okay, thank you. The next question, doctor. Concentrations of the agonist clomotrol is similar to that one used in asthmatic patients. It's divided by 2. It has to go with an inhaled metagonistic, and as it is related to TB complications. Yes, we started doing these trials. It was very important to try to identify if there was any similar to other infectious diseases at experimental levels in mice, and we didn't find much. And then later we had to try to regulate the doses for animals and then adapt them for humans, and that was a good guideline. That was equivalence. It's very similar. We had the patients with asthma in the case of probuterol. Last question. Taking into consideration the vagus lung reflex, how do gonna do the reduction of the activity of the zipaline? Yes, most of these anticholinergic drugs for as relaxers of the smooth tubes, especially in the digestive system. They have to do on the carinic receiver level. One part of that we didn't study and we want to elaborate on that is that probably during the early stage of the TB infection, mostly we need to have muscarinic receivers more than that are being expressed. So in this sense, since they have different activities, well, probably this increase on day 7, and I showed you in the codification acetylcholine by HTBC, maybe that's when it's basically done to muscarinic receivers, and then you have an activation effect. So I'm just speaking hypothetically here because no research has been done on this, but I think it could be done. As for the antagonist, nicotinic antagonist, probably what we have the most there in the human activity is nicotine, which is the closest receiver and one of the most popular toxic ingredients in the tobacco smoke. So having to see nicotine with the metabolism of the mycobacteria, see then the same as acetylcholine, we can see the nicotine has a very similar effect on bacteria.
Entonces también un supresor de la activación macrofágica y es por eso también muy probable que los pacientes con mayor propensión a desarrollar tuberculosis. La razón de eso es principalmente la
nicotine, but we know nicotine is an exogenous agent. So we call this nicotinic receiver because it has its affinity to acetylcholine, but also nicotine the macrophagus also allows infectious disease, not only TB, to be able to become stronger in patients who smoke. Thank you, doctor, for your presentation. No, thank you for your attention. I can tell you this event is being supported by Pando with headquarters in Mexicali and offices in Ensenada and Tijuana, also by Vicen company, which has headquarters in Guadalajara and offices in Ensenada, distribution nationwide.
Ahora le damos la bienvenida al doctor Carlos.
Now we welcome Dr. Carlos Martín. He studied medicine at the University of Zaragoza and belongs to the school of Professor Gomez Luz, with whom he does his PhD on the bacterial resistance mechanisms. He has a PhD on biochemistry by the University of Paris. He also part of the CIBER for Respiratory Disease Center in the Health Institute Carlos III, also works on investigation development of living vaccines for TB. He and his team have worked and characterized the MTBVAC vaccine. Today, He works in different investigative research projects financed by the UN, European Union, and collaborating with different research groups in Europe, Africa, and Latin America. And he has been working for over 30 years in genetics of microbacteria. His presentation is titled MTBVAC, the challenge of improving protection against transmissible TB after 100 years of using BCG. Doctor, we remind you, you have 40 to 40 minutes for your presentation, then we'll have a 15-minute Q&A session. Thank you, Dr. Perea. And Dr. Muñiz, thank you so much for allowing me to participate in these talks on TB that are being organized by the Autonomous University of Baja California. Today's presentation, I'm going to be talking about the work that has been going on for several years. And a lot of people have been involved. So it's a privilege for me to be able to show the results of all this hard work, which is the development of an idea of how we can attenuate the TB bacillum in animals and in humans. So we have crossed many bridges. You will see throughout the time that with the help of the small companies, now they're not large companies that work in the development of vaccines for TB. And the idea is to see, we're about to reach the third stage of efficiency age, this MTBVAC. So there's just a summary of what we have seen in the previous presentations, that up to the year 2020, that's when COVID hits, TB was the largest pathogenous, human pathogenous, and out of in the last 200 years, we estimate about 1 billion patients have died of TB. In year 2020 is left behind a little by COVID, but now we can see here, and since in recent years, this reduction of TB cases for the first time has gone up, and what is most important and more dangerous, treatment has dropped too. So we don't know what to expect. It's important to research more drugs and diseases that can be curable. Is the operation of new multi-resistant strains that appear basically in areas that are related to the HIV, and also the different strains, rifampicin resistant strains, and also to second generation drugs. That's why we lose treatment capacity. So even the incidence of TB may be in developing countries, mostly in Southern Africa and India, a third of the world's population, and Indonesia. We are concerned, especially in Eastern Europe, about this, Western Europe. So how we are concerned about this. We need to be able to find a good control. BCG is a vaccine that has been implemented around the world for 100 years, but it does not protect against the respiratory form. So it's essential to develop new vaccines that are more effective against these respiratory forms of the disease, because BCG protects in children with disseminated form or in the meninges form, protects them against that, but they don't protect against transmission. So I'd like to quote Dr. Julius Jung, that says TB is very complex, and we need to know the immunology, as is in the previous presentation. But we also need to know the immunology. We need to find vaccines that can protect us and will allow us to understand how we can have a population that protects us or that it does not. Because it's in TB and malaria and AIDS, there is no correlation protection. So we need to know that a vaccine protects and see the different mechanisms. So the trials that we started with MTBVAC, they've been going on for almost 25 years, because they started with the trial of the study of this research of multi-resistant strains that were spread within the HIV positive population. Is in a mutation that you see here later, and then in collaboration with outsourced labs, we had some mice modules. So we talked to Dr. Rojas and many other labs. Our lab, we work with the neonatal mice model, collaboration in England, and also in collaboration with the Netherlands and England in monkeys. So we have seen in the vaccine is so attenuated with CG, and is more efficient than the models that we see in the mice and the monkeys. So what's important the most, we can see and the activate the second mutation. So we know we're not going to have the same virulence. So we need a little in the company that is BioFabry that we founded in Spain over 1,000 years from Zaragoza, where we work, and they are the ones that decided to take the lab stage to clinic stage, and they industrially produce. It's very important because for BCG we have different strains that are subculture and they are different. So it's very important to have industrial production and stable production, large scale production for the clinical trials. Since 2018 to 2019, we have the clinical stage that we started the first time trials on humans and then in adults and then in babies. We discussed this in South Africa because it's an endemic country. Then we go to phase 2 with 99 babies and 144 adults, and then we're ready to go into the efficiency, test efficiency in countries with high incidence such as South Africa, but also collaborated and go to see the immunology and Madagascar. So we see the diversity of all those vaccines against TB that are now today in clinical trials. They're very similar to the vaccines that we have seen for COVID. These are viral vectors that could be adenovirus, MVA, which is a virus, the chimpanzee adenovirus, influenza virus. When we have this virus, we have genes that are 1 or 2 genes that are specific to TB that increase the immunity. But we don't know if those antigens are essential for protection. Same happens with adjuvanted. M72, we have the prototype for vaccine with AS01A, and the one that is being used right now with the Ulster herpes in our media, in our region. So we see the active isolated bacillus, but there are now some candidates for other inactive bacteria that are in phase 2. Then we have the BCG that has been used for the last years, the recombinated BCG, and since we are looking a few genes, we decided to go to a clinical strain of TB. What we need is a RNA. So we have vaccines, and since we don't know the antigen that may protect against TB, it will be very difficult to get protection with these limited antigens until we know what is the protection correlation. So for antiviral, we started working with the genetics mentioned in 1998, and in year 1988 is when we started working with Dr. Ezequiel in Pasteur, and there is when we decided to do a trial based on an attenuated strain from a human originated pathogen. We selected the lineage, the most distributed lineage in North America, South America, Europe, and Africa will be lineage 4, and which genes to inactivate. We started from a gene that was essential for the virulence of TB. According to the case in Spain, and then we have the fat lipid gene that without those lipids is not virulent. So obviously to debilitate the BCG strain culture, as what happened when distribution in Brazil, Russia, and Japan, they had different variations. We wanted to have industrial production that will allow us to have these vaccines homogeneous or unified. When the gene that started to deactivate, and we were discovered first in a pandemic that happened in Spain in the 1990s, when we didn't have a retroviral treatment for HIV. So we saw one of the strains from cows would be transferred to humans because an insertion sequencing that would increase the transcription sequence that is essential for the virulence of the pathogen. So we tend to use this without. So what we wanted to do with the tools that described 10 years later in the Pasteur University by Dr. Brigitte Zigel, and they discovered the inactivity method with inactivated CFUP, and they also discovered that the PDM lipid is essential for the virulence gene cluster. So this is synthesizing this lipid, we decided we cannot have a reversion of virulence. We will need to have a horizontal transmission. In case of TB, we don't have. So now the MTBVAC is in clinical trials. It's a lyophilized treatment with BCG, and that can be distributed and kept for 4 hours. And it's a single doses. So in our lab, fundamental in the construction of the first mutant, and then for the final production of MTBVAC. It took us about 4 years to get here for the final construction. So if you see the MTBVAC comes from this fourth lineage when we compare to the Bobby's genes with loose amino genes, and especially in BCG, what we have seen is that we lose this region that contains the genes ESAT6 and CFP10. They're essential for the protection, but they are part of the mycobacterium TB. And when we see numbers, epitopes, the comparison the MTB and BCG, and they concentrate much more on this. So when we see BCG, it just produces these two proteins. But when we export MTBVAC, when we export, but it does not produce it, as you can see later in animal models. So currently, we're very familiar with the genomic level with Professor Stephen Cole and the proteonic level and methodological protein, what MTBVAC is. When we compare to wild TB, we see that it has some lipids, and the outer part, the exterior, contributes with the anti-immune system to guide it from the anti-immune system. So it does MTBVAC control these lipids, and so it does not have these lipids, and it exports proteins by the PFP regulated that it was used for different other vaccines, and basically the PFP10 proteins, but does not export the SE6 protein that is essential for virulence. So it drops the immune response for TB. It breaks the phagosomal rupture. We have the contrary effect. So it's very important to go from the trial to the development. So the University of Zaragoza just signed with this company that this is our principle, that the development of the bacteria was the condition was to make sure it was affordable for developing countries, and so from there, companies financed by the Spanish government, we managed to develop this vaccine, and at industrial level, we use CZ veterinarian. Now it's called CZ vaccine. Hydrofabric has been the factory that has been assigned to producing this MTBVAC vaccine. So they were experienced with working with mycobacterium bovis. So the virulence of the bacteria it's nothing that would scare them. So they had much experience in the development of vaccines for veterinary purposes, but that was transferred to human use. So currently, in collaboration with external outsourced labs, we have usually vaccine prototype that goes into trial stages. They never go back to the animal stages because the company will pay the hundreds of millions that cost for the clinical trials. We're going to go with public monies and the different sources from maybe the European Union, the EH, the WHO, maybe the Gates Foundation. We need to prove in animal models that this vaccine is better than the current BCG, and that's what we did. As in safety, it's the same as BCG for protection. In mice, we've seen that it protects better in different models, especially in VL6 and in the newborn mice. It has a higher vaccination, higher immunity to anti-active and PPD notification, and the guinea pigs when they're vaccinated with BCG, and we have better protection here. And also for the non-human primates adults, we have seen high protection, and this high protection is linked to the recognition of these proteins. We have some other natural models that have not been published, and we see that testing this in mice in the lineage 4 that protects against the Beijing strains and other strains from the modern lineage. So we believe that it will be a protection against the different lineages. So we move past to the clinical trial. They started by the Francois Despertini, who was experiencing vaccination using vaccines against malaria and HIV and TB. So here for the first time in humans, we managed to have a vaccination to adults that are mostly medicine students from 18 to 45 years in age. They're volunteer with double blind. It was a double blind trial, and we used 5,000, 50,000, 500,000 bacteria. It was escalated with controls to make sure that everything was going well, to increase the doses. What we were trying to do here was the safety. It was similar to BCG, and also the antigenic outcomes against TB agents. So this was the results. This was the outcomes. So it was the same as the BCG. It was counseled by TBVI, by the regulatory agencies, that we're always gonna be comparing against the BCG vaccines. So the immunogenicity trials are gonna conclusive because they will see they're not decisive. And then day 28, when we have the peak in adults, we'll talk about babies later. In the first month, when we hear the lowest doses, stimulating with Mycobacterium tuberculosis, what we do is we measure the CD4 that are capable of producing three cytokines, IFN, IL, and TNF. So there is no protection correlation. We know it's essential, the protection, and IFN for TB protection. So we see the peak in day 28 by increasing the doses. We see that each doses there is an increase of this signal of TB4 compared to BC4. There's a big difference. So we see a trend, and that's this security and this immunogenicity that I given the authorization to take this to clinical trials in endemic countries. So 25 kilometers from Cape City, we have Gloucester, which is where we studied the Oxford vaccine that was published in 2013, and that was a vaccine recombined with MVA virus. Even though it didn't work as a vaccine, they had the whole system to detect to trial new vaccines. There is a great team by Dr. Hassely, Tom Scriba, where they have some immunology labs in Cape City at 140 kilometers from the clinical trial site. And also Dr. Michel Tamaris, who is the lead researcher for this project. Since this is for babies, it was financed by the NORAD Foundation from Norway for the clinical trial. Here the incidence is the reality where we have the MBA trial, an incidence of 2 to 3% of all the babies living in this area, they have tuberculosis. So the trial was designed the same way, not as in Sweden. In South Africa, we usually use phase 1 is not done. So what we did was to repeat with the highest doses of MTBVAC, a vaccine of 9 vaccine shots for 9 healthy individuals in South Africa. We saw it was safe. We started vaccinating the phase cohort, the second cohort, in the third cohort, and then with all this control system to make sure that everything was well and the babies were responding well to the vaccine and they had no side effects. When we saw in this trial, we said the low doses does not work very well. Now we see this the CD4 that are polyfunctional with the immunoglobulin and the TNF alpha, IL-2 and IL-17. We see the BCG, we have the response on day 70. That is the same as what we saw here, 10 to 4. So we see in the 10 to 5, the same concentration of BCG, response of CD4s is much higher. Here we eliminated these doses. And what we saw here is that after a year, that also did
Algo que sorprendió muchísimo porque nunca se había visto en ensayos clínicos de otras vacunas fue la conversión al cuantificador. Todos los que trabajamos en tuberculosis sabemos que la prueba del cuantificador que se utiliza es la conversión de interferón gamma de nuestras células blancas cuando las ponemos en contacto con las 3 proteínas, esas 6, y lo que medimos es la producción.
And we see in the LISA, we do have the quantiferon gamma. We said that the identification of these proteins. So BCG did not have these proteins. But we saw with the low doses, there was a small group of babies. In 10 to 5, we see high concentration BCG, we see up to 80% recognized in these proteins. ESH6 and CFP10. Yes, it will reduce. And after a year, there's a quantiferon will produce the disease, but for us, it was the result, the same result we had with the animal model. Yeah, those who and the monkey models are protected. So we have great hope in this data. This was published also in the Lancer Respiratory Medicine, and also Dr. Michelle Tamaris was the lead researcher, and we see that the highest doses has most, but we see the response was differential, and it was relatively different from the doses 10 to 5. So we chose these doses for working later on, and then we see in the next clinical trial another doses. So all this data in an endemic country. Why was it done? Because it's the only place where we will be able to study that later, the efficiency of vaccine. Where are we now? We have is a phase 1 is adults. In Switzerland, we have 1B and 36 babies plus the 9 adults. Now we have been concluded, even though the data has not been published, of a phase 2A in babies in the groups that went from 9 to 25 per group, and eliminating the lowest doses, increases to higher doses to see the plateau of the immune system, and also in adults that were infected, non-infected with TB. See, this is what we have the results, because in the future I would like to see, even if we talk about clinical trials in teenagers and adults, I think it's a very important target for eliminating transmission of the disease. So this phase 2A trial, it was done with 99 babies in Cape Town. When the cohort that was used for the efficiency was from 10 to 5, say the 10 to 6 was safe, without any failure in the vaccine that we could put 10 times the doses, that see the vaccine will be safe, but immunogenicity that we like the most was for the cohort 2. So the adult trial that was done in adults infected with TB, the groups were smaller in phase 1 with 2A, because even never been tested, this vaccine was never been tested in such high doses with infected people. And we said 10 to 3, 10 to 4, 10 to 5, 10 to 6, and positive, got different positive and different negative. So we don't have the data to present this. It's been financed by the US, and it's coordinated by IEMI, which is an American foundation, a non-profit organization. So what we have seen here is that 24 at the end, which is 25 in each one of the groups. Here the data are much higher for the number of babies that have been vaccinated. As you can see here at the end, halfway through, this is the COVID pandemic, and it had to be shut down for months, and this would be the first baby that was vaccinated in 2019, and the last baby vaccinated almost 2 years after. So we compare this to the studies with the COVID vaccines. The phase 1, 2 was done basically in 2 or 3 months. We had the complexity of working in patients where they're endemic of TB, or they also have COVID problems, which is the way we did. Currently, phase 3 is Dr. Ingrid Murillo, who is coordinating all these trials. We're gonna start with the protection phase. For that, we're gonna vaccinate half the newborn babies. BCG is used for the newborns, so it will be the placebo. Well, not placebo, but babies vaccinated with BCG. Half the group will be vaccinated with MTBVAC. So safety will be seen in the first 100,000 vaccinated babies, and we will see in Senegal part of the population, the immunity that will produce. Just to see in different populations, we have different reaction to the vaccine. We also in Madagascar, but the efficiency with the highest TB incidence will be in 4 sites, different vaccination sites in South Africa. The project is financed by the European Union and part, and also by BioFabry, and a great number of researchers are involved. In May this year in Galicia, we have the first meeting of the project to do the kickoff meeting. Well, we had here all the groups from South Africa, Madagascar, South Africa again, people from our lab. It was the beginning of something that after so many years of working in the lab, we were completely excited. So now this is the time. It's time to see if this vaccine is going to protect all the against all the respiratory forms of disease. Now we're going to tell you about the work that we're doing in the basic research lab. We want to have a vaccine that can be translated into the population that has we want them to protect, but with BCG, we know that has non-specific effects that are now very fashion for the vaccine. What are these? These are not only protected against TB, but also does BCG, reduce the mortality. We know it protects against bladder cancer. It's actually a treatment for bladder cancer. We have studied the mechanisms to see how these non-specific effects work, and maybe you can work for asthma and see, you want to see if they may interfere or not with our vaccines. We'll also discuss how other routes of administration to improve the effectiveness. This is in research our lab since '76. Is when we started with BCG for the bladder cancer, and then we have seen in different models and mouse models that can protect the best way it works. Is year 24. This one BCG carried by the basically entail that it has a immunity for the cells, and this the monocytes adapted epigenomically speaking to develop all the cytokines that protect against other diseases. So we have studied this in Mycobacterium TB. They have seen that it can protect against Candida albicans, and also an MTBVAC protects the vaccinated streptococcus pneumonia, and also has a therapeutic efficacy against established asthma. And also, we want to see if it interferes or not, or interacts or not with our vaccines, because when the vaccines are will be used since the newborns in the first 24 hours of life. And so we want to make sure it does not interfere with other vaccines. So as I was saying, the Merlin classic is classic for bladder cancer. You can see in the model in the box, and we put we implanted tumor cells in mice, and then we do follow-up treatments with BCG and MTBVAC. And what we see, the response to Th1 is higher or not, and we can see the survival. Say in the model day 3, we implant the tumor on day 0, they planted on day 3, and then we have the BCG mortality start to drop here. And we see MTBVAC has better protection. And recently this year, a team by Nacho Aguilar, who controls the specific effects and the vaccines, and what they have published is that even when we inoculate the tumor even later on day 6, BCG does not work. MTBVAC works at 80%. But when we add anti-PD-L1, which is when we don't have BCG working, we see the protection is 100%. Why is this important? Because these form tumors, we see BCG does not work, and treatment for see the extirpation of this bladder. So the MTBVAC treatment and anti-PD-L1 could help people whose only option is to have their bladder removed. We might be able to save their organ with this treatment. So we have also seen that the best efficacy against bladder cancer is because these MTBVAC cells against the BCG, they persist for longer in the bladder. And we have also seen that BCG, these BCG, fluorescent and MTBVAC, they are more present in the bladder and also in the glands where the nodes. When we see in the region that where the one that use this, we lose this protection of MTBVAC. That's why it's important. In this MDR1, it has MTBVAC. It does not have BCG. And the trials with the MTA team, we say the mice model, they are vaccinated anti-BPS, so we say we have more cytokines. We saw that mice infected vaccinated with MTBVAC with the streptococcus pneumoniae, they had lower death rates. What's very important is that study the lymphocytes in humans. What we saw was that with the MTBVAC, there was dose dependency in the production of interleukin 1B and IL-6 and TNF alpha. This is stimulated when we are vaccinated. And what we also observed was that in studying the methylation of the histones, we saw methylation of these promoters that are in front of these interleukins and TNF alpha. This is important because it uses epigenetic reprogramming in human monocytes, which is identical to that granted by BCG. When there's a baby, a newborn is vaccinated, we vaccinate with 500,000 bacteria, could be BCG or MTBVAC. All the cytokine promoters due to the epigenomic effect, what it produces is a higher increase, and what it does is a second infection is ready for a second infection. they will be more protective and the response will be faster. Also, for example, also Ignacio Aguilón and our lab in collaboration with Raquel Tancon, who was the first researcher, is in models where the lab mice, if we make him allergic to flour, we say it's Synaphyll's production, and also when we treat them through respiratory administration with MTBVAC or BCG, we see the number of Synaphyllus, and also the dilation in the lung become the heel or the lungs heal too. And we also saw the model that tells we tried to work on to see analogies. We see inoculating this, we can produce the alveolus was damaged. When treating with MTBVAC and BCG, we could produce and reduce. What we saw was the Th1 response, very Th1, but powerful Th1 response. It also affects and the asthma response. So we also saw in this article that the small size of MTBVAC, because the mutation what it produces are bacteria, almost half of the BCG, as it can be done on spray better than the current BCG. And also as a non-specific effect, we see the mice model when they are vaccinated with BCG, previously vaccinated with MTBVAC, and then we give a single doses of diphtheria, tetanus, hypertusi, a cellular hypertusi. So we see a high production of diphtheria toxin antibodies, higher production of antibodies for tetanus and for pertussis. So, and also cellular immunity. See, we have 3 vaccines. After vaccinated with BCG and MTBVAC, you will see here how all the BCG and MTBVAC vaccination will have a response of IFN, the lymphocytes that will be better against protection against the 3 proteins. So there is no interference with normal vaccines for babies, and they have a stimulated effect. And so in other epidemiological trials, these are not epidemiological trials, only ecological trials. But what we see is that in countries where people are vaccinated only with bacteria, tetanus, and cellular pertussis, is much larger just in countries that is vaccinated with BCG and DTAP, places where they vaccine with BCG and the DTWP, then there is no difference. So in countries when they vaccinate with BCG, there is a better response to pertussis. This was in collaboration with Nacional and the Brazil University in Camille Lodge from France, and our country, Federico Martín, who is a pediatrician, who has helped us for the vaccine trials. On another, we have the other routes of administration. MCGB is intradermic administration because that's the only way. That's been done for 100 years, but now the regulatory bodies will ask you to do the safety is better, protection is better. But if you want to change your routes, it will be a challenge, but it's a dream because in polio we have antibiotic polio vaccine, and it reduced polio in which is a digestive cases and was reduced in case of the US. And they had to use artificial lungs for patients with this. Well, polio has been almost eradicated because we have a vaccine that is administered via digestive, with digestive administration, oral administration. because we're talking about a digestive. So, and it's very easy to administer. So what is our dream? And for polio, we can do this orally, and TB is spread through the air. We want to make sure, find different ways of administration, but also BCG and TB used through the respiratory tract. I think it's a good protection correlation. Although currently BCG has not shown an TB. We see that this responds much better to TB infection when the inoculation of the vaccine is through the lung. This Framberg has studied this in the Netherlands in mice models, use the TB infections and see how it protects much better. And so upon long administration increases the protection in long terms for monkeys against the BCG early in 2021. The Framberg team also published using an MTBVAC. They haven't done the challenge. They're looking for financing for this. But at an immunological level, we see that there is TH1, TH17 is similar to the BCG in the lung with MTBVAC, and the effects, the non-specific effects that were produced in BCG can be reproduced with MTBVAC. So this is something that is very hopeful, and we think is very interesting. What is the idea since the very beginning of the presentation? That's what we wanted to do with MTBVAC with, as I said, since 87, we started studying this, we started studying the genetics in Pasteur in 1997. We started the motor-resistant TB, and we kept working on this until 2008 when we have a lab. They've got a person to go do the clinical trials. So the idea is that a vaccine that is a single dose, that it's easy to distribute. And then we have the MTBVAC experience that can be distributed better. It should protect against respiratory forms. As we know, they can be distributed in endemic countries which is much needed at an affordable price. That's our dream. Right now, we expect this it could be economic expression, and hopefully the picture will be through the respiratory tract. So well, we expect to see the timing between the COVID and COVID vaccines. We see that since 1982, Robert Koch discovered the tuberculosis virus, and COVID-19 virus was discovered in 2019. It was sequenced in 2020. We had the first vaccines in 2020. That means a year after. But in the case of TB, it took almost 40 years. And how many efficiencies we have being used right now? In COVID, we have 18 vaccines available. By June 2021, the number of candidates, we're talking about over 100 candidates. And then for TB, we have 14 investment. We're talking about 117 billion euros. We're talking 107, meaning we have to spend much more money on COVID and number of deaths. We see that it could be 1.5 million in countries where TB is endemic. Well, it's very similar. The first data that has been identified in the own WHO reports that see COVID is dropping, and TB is persists, and it's been going on forever or for a long time, and it's a disease that we cannot eradicate if we don't have proper diagnosis, proper treatment, and proper vaccines. As you see, is a work from a lot of people in different collaboration with different organizations. When the Pasteur University Institute, we work with Stephen Korb in Switzerland. Currently is the Institute Pasteur director. Marcel Baer is another one of the main promoters of this. Also in France, we have worked with Christophe Guilhon He's in Toulouse. He works with the lipids. All the FoVI studies are done in the Health Protection Agency. In Sydney, we have worked with James Tricas. In Mexico, we have been working with Dr. Rogelio Pando. We have the vaccine prototype, and we had the first result that the use of this. Also, in Monkeys in the Netherlands, in Spain, we are working with Cardona and Maria Jesus Garcia, and in the Netherlands with Mihail Desi, and this is the work of many people. Then here we have the lab where we have a dream team. We'll have Nacho Aguiló, Jesus Gonzalo. We'll have the superintendents of the vaccine. They are the experts on immunology and basically mostly the genetics. And thank you so much for your attention. It was I'll be here for questions. Okay. Thank you so much.
Agradecemos al doctor Martín por su interesante conferencia y ahora vamos a dar espacio para las preguntas. El gran doctor se ve toda una gran trayectoria en ese desarrollo con tantos años de trabajo con la vacunación. La primera pregunta que tenemos es...
The first question we have is about the expected outcomes of phase 3. You said that MTBVAC has better protection against compared against BCG, but how could it affect the incidence of complications? We may expect an unexpected outcome for phase 3. You're talking about efficiency against TB, is that what you meant? Yes, well, it would have been estimated that for the efficiency to be able to measure over 50%. Versus BCG, we're going to vaccinate 3,500 children with it would be a double-blinded test. So we're going to diagnose cases. We're going to keep all those in closed envelopes, and then when we have 50 envelopes, we're going to open the envelopes and we'll see which children were vaccinated with BCG, which were vaccinated with MTBVAC. In the first trial, we'll see if the vaccine does not work, utility, and then it will be eliminated, and then the trial will be closed. But if it goes well, then we'll follow up 100 vaccinated. Once we have 100 vaccinated people, and then we open the envelopes, and if our dream becomes true, then 80% that were vaccinated with BCG and 20% will be vaccinated with MTBVAC, and we'll see. And as we want to see from the vaccination period, 5 years, and follow-up period, 2 years, and so it's 7 years, depending, of course, on the number of cases that may appear. We are having an estimate with the pre-COVID era. We don't know what to expect because the incidence is going up. But the data we have are data from year 2013. So that's 2-3% of babies. They have a TB diagnosis. I wouldn't know the penetrations in the audience. They know how difficult it is to come up with that diagnosis. So for the diagnosis, we have 3 doctors that will see due to X-rays, culture, or symptoms. It is a natural case of TB. That's the most difficult part in babies. In teenagers, it would be a lot easier because it's our dream. Also in teenagers, after the PCR, like it was so expensive before COVID, that to be with sputum, we can do an PCR and a spare without the insertables in the nose, simply with the sputum. If we could vaccinate 70,000 people, we did with COVID, and see in adults, we wouldn't need to wait on BCG because when we see a placebo and vaccine and PCR positive, you would have a vaccine that would prevent the transmission, because like in COVID, we have COVID in the mucus and we'll continue spreading this. But we could study the transmission of TB if we do diagnosis researches on PCR. Great. Next question. What kind of idea? What? You're talking about immunity, and we're talking about classic immunity, or have studied the response of interferon gamma because we know that people without interferon gamma are not protected against TB. So that's essential, that for the protection, but we don't know what's the response. The idea of using a vaccine, a live attenuated vaccine was done for the yellow fever and was done empirically. It has been done for 70, 60 years, and they have protected, because we know we need antibodies, but also need some cellular immunity. When in our case, we haven't seen any antibodies, so it was difficult to go to see the antigens that were the NRA. Will be a problem in the future because we don't have a good a rule in TB that we know that will protect. So that was part of the positive side of what Dr. Jiang was saying. They said we need vaccines that protect, but when we have a series of individuals only with and others that don't, we'll see which identified proteins are present. We think that would be essential. I hope that I'm answering your question. Macrophages, of course, but a trained response, that would be the innate response. But we would like to have a trained response from CD4, CD8, and respond to antigens that we don't know which are, and so on. Next question is, if you believe the success of the vaccine has to do with the outcomes, we plan to have a booster after a certain time? You're talking about the different administration, inhale administration and under skin. Yes, a TH17 response that we see in the monkeys has a protection is the one that gives higher protection. So yeah, the regulatory bodies will have to always everything that has to be inhaled for instance, for the flu vaccines. We're afraid of the reference to the brain. So we will need to demonstrate very well that we are talking about vaccination. This is a healthy individual. We're talking about babies who are very vulnerable individuals. So also in the case of serious asthma, we could be used as control that it does not produce any side effect on people who are volunteers. They have some sort of pathology, and then would open the field for better protection. But of course, especially we're not afraid of TB. If we were afraid of having a TB pandemic, everything would change, but that's not the case. Yes, we have many more volunteers for this, right? Yes, and volunteers are, well, are amazing. In the case of babies, it's the mothers. They have to give the consent for their babies to take this. A couple months prior they give birth, they have to give consent. In the case of teenagers from 18 to 45 years of age, and they were usually voluntaries. The regulatory authorities, I don't think they're going to allow the use of sprays that would take a lot of time. But we know that our dream would be to accelerate right now the subcutaneous injection, and then to reduce the number of cases as soon as possible, and then change the method of administration. Doctor, regarding the non-specific effects, when you say the treatment for cancer and asthma is a single doses, so you want to have multiple doses for treatment? No, these are several doses for asthma and for it's to treatment for a week. Introduce 200 milliliters in the bladder for 2 hours and repeat, and it's done again in the second, third, or fourth week. When we have the immunological response that we expect to Th1, then has to do with the tumor. For respiratory cases, where we need to test and try it in different acute stages of asthma, but it's a lot easier to go with an inhaler when you have an asthma situation than getting a shot. Then in the PCG, when you see in animal models, it persists in the nodes for as long as BCG, and BCG in cases we see in the HIV, we have seen that we can produce, it's like a latent infection of TB that would keep activating the immune system. Thank you. Last question. do you think that the main idea barrier for getting a TB vaccine is the lack of investment or the money allocated by the government to work on this? No, or the characteristics of the bacteria. No, the characteristics of the bacteria is very important because the HIV, we have the virus the last 4 years. We don't have any candidates for vaccine. For instance, for TB, we have 14 candidates that could be accelerated. So far, there was very little understood, but BCG, we have made a big effort to vaccinate hundreds of millions. And we works because we reduce mortality and serious cases, but if we just generate it with a confidence that now our MTBVAC, that's our baby. The dream would be to have good investment. Yes, and we're going to have efficiency in a country. We're going to ask the WHO. The WHO will ask for trials in different countries. And also for an authorization, we need to say that we are capable of producing all the millions of doses that are needed by Fabric, which is a small company. Now has reached an agreement with Bharat in India. They have been able to produce 600 million doses for vaccines against COVID. So the idea would be an association with no profit organization, or profit that also has a benefit as producing more vaccines, but it could be produced industrial level. Thank you, Dr. Martins, for your interesting conference. No, thank you for having me. To all the attendees that are interested in getting an attendance certificate, the deadline is next Monday. The requirements and terms and conditions you can find in www.remitv.com. I want to thank our sponsors, Valtro and Vicent companies. I want to thank interpreter Claudio Valencia, who was interpreting both conference from Spanish into English. We also want to thank the English conference. We can find it in RemitTV YouTube channel. I want to thank all the support to our CEPA Center. I want to thank you for all your support. And all of you who were here with us. I want to invite you the next week for the 8th and last session of this forum. Tuesday, November 22nd. We're going to have the participation of Dr. Sebastian, who is the lead of the TB Research Center by the University of Marseille, who will give the presentation Evolution and Economic of the MDR tuberculosis. We will also have Dr. Cuauhtémoc Licona, who is a researcher for the system lab by the Technical Institute of Monterrey. We want to invite you, please follow us on our social media. Have a wonderful day. Thank you.